So this is joint work with Tirtha Suresh from Google and Yihong Wu from Yale. We will talk about sample complexity of population recovery. Okay, so let me introduce the problem. So I'll talk about it twice, in the beginning and then in the middle. So let me first, as a first example, let me phrase the question as follows. So suppose we are collecting polls from the population, asking, population of people binary questions. Things like, what chocolate you like, vanilla, or, sorry, what ice cream you like, vanilla or chocolate, right? Do you vote Republican or Democrat? Do you favor Real Madrid or Barcelona? And things like this, right? So, and then we collect this data carefully. And then at some point later in time, we are asked to estimate what is the fraction of population with the given profile, right? With the given 0 and 1 pattern of answers. So that's the question of population recovery. Of course, if you have perfect answers from the population, then there's nothing to do, right? But the twist is that population, when you sample the answers, each answer can either be erased, so the person may refuse to answer the question, or he might make a mistake or lie with probability epsilon. So this is a noisy data, and you're trying to estimate the fraction of population with a particular answer. Okay, so it turns out that there is a standard result, or there is an older result 5 years ago from Dvir et al., who showed that the problem of estimating one atom of unknown distribution is equivalent to estimating the whole distribution in L-infinity distance. Okay, so again, so this is so I keep the setting here for those of you who are late. So we are going to be interested in the sample complexity, namely the minimum number of samples which you need to take in order to estimate the 0th atom, in this case, the 0th atom of unknown distribution with precision delta. So delta throughout my talk is always going to be the precision of the estimate. And okay, so I put the quadratic loss here. And this is a minimax risk, meaning this should hold for arbitrary distribution pi on the binary strings. Okay, so what's the history of this problem? Well, it appeared first in this paper of Dvir, Rao, Vidgerson, and Yuhaidayov. And the motivation there was not what I said now for estimating the fraction of the population with the particular answers, but they were actually interested in learning what's called DNFs. And this is, I don't really understand this motivation well, but it's some kind of learning of DNFs with restriction access, where you observe basically reduced clauses. So they proved that in this setting, in the setting of erasures, so when you erase certain answers, this is called lossy population recovery. So in the lossy population recovery, you can you can estimate with polynomial number of samples in the precision. Okay, but interestingly, their algorithm only worked above a certain epsilon. Then there was an immediate update which extended the range of epsilon. And then, very importantly for our work, there is a work of Ankur Moitra and Michael Sachs in 2013 who extended the estimator to all epsilon less than 1. So for all erasure probabilities less than 1, you can estimate from polynomial number of samples, right, within the precision delta. Okay, so now noisy population recovery is a slightly different topic. In all the works on noisy population recovery, all the authors always put an additional assumption that the support of the unknown distribution is k-sparse. And we will hear a talk next from Zhang on this problem. But the important conclusion from a series of works is that you can estimate with the number of samples, which is polynomial in delta, under this extra assumption of sparsity. Okay, so what is the results of this work? So here's the summary. So first, for the lossy for the lossy population recovery, we show that the number of samples, we prove that there exists an estimator which estimates with 1 over delta square, and which is the parametric rate, if the erasure probability is less than 1/2 and above erasure rate 1/2. Surprisingly, you need a little bit, the speed of this grows with delta with a bigger exponent. Now, Yihong told me that I should really stress that this is an elbow effect, so I'm stressing this. Now, for me, what's interesting here is that this estimate is actually dimension independent, so it doesn't matter if this upper bound does not hide any constants depending on dimension. Okay, and then furthermore, this estimate is actually tight in the regime of high dimension. So you cannot improve this. Okay, so for noisy population recovery, again, we prove that a tight estimate on the sample complexity, but in this case, it's a very depressing result because it shows that if you want to estimate from, in the noisy setting when the responders lie, right, then you need exponential in dimension, in the cubic root of dimension number of samples. And that explains, by the way, why all the previous works actually assumed in addition that the distribution is sparse. Okay, so let me tell you about the key tool that we used here. So this was a byproduct. I mean, we really were interested in solving that problem, but in the process, we noticed that we actually discovered something general. So let me explain this. So let's consider a general problem of estimating a linear functional of an underlying distribution pi. So we have pi, right? And then we're interested in estimating expectation of pi, expectation of some function h under pi. So I will denote this as this parenthesis pi comma h. It's a dual pairing, right? So now, unfortunately, we don't get samples of theta itself from the distribution pi. What we do get is we get some noisy observations of theta, right? So in information theory, we would say this is a channel. Okay, so now the model is the following, right? So you generate IID samples from pi, then you observe correlated samples of xi, and this is what I denote by this notation. P sub pi is this mixture distribution, and with tensor n, meaning theta is regenerated every time. So this is very important. Theta is not generated once, but at every sample. Okay, so, and then we're interested in the minimax risk. Okay, so what can you say about this bound? I mean, majority of people here, I'm sure, know what to do for such questions, right? You do LeCam method. So in particular, if you find two distributions, p and pi prime, such that total variation distance after you take tensor NIID repetitions, right, between them is less than 1/2, then the risk should be lower bounded by, by the gap in the functional value, right, squared. So this is a lower bound. Okay, so let's keep going, right? So let's try to tighten this bound. So first of all, this estimate, total variation of n-fold product, right, we can upper bound by triangle inequality by n times the total variation between single letter expressions, right? And so now it makes sense to optimize the choice of p and p prime, right? Because remember, our lower bound on the risk is the square of the gap in the value of the function, all right? So let's select the best possible pair of p and p prime subject to total variation constraint, right? So okay, so we get this function which I call delta min TV. Okay, so I introduced this parameter phi instead of talking about the mixture of pi, right? So phi is just the matrix of these conditional distributions. Okay, so we get this lower bound on the risk, which is delta min TV squared, right? Delta min TV is just this linear program. Okay, let's talk about the achievability part. So what we'll do is we'll only consider what's called linear estimators, right? So this is the estimator of unknown functional of the prior, which is constructed by taking empirical average of certain function g, right? Okay, so what we will do is we will analyze bias variance trade-off, right? So we split the expectation into variance of g and the square of the bias. We upper bound the variance here by the L infinity norm of g. Then we take square root. So we rewrite this as this expression. Okay, so now we want to optimize right over g. So this is a standard thing, right? So you're just optimizing bias variance trade-off. Okay, so but the only funny twist that we decided to do is when we are optimizing infimum, when we are computing the best estimator, right? We said, why don't we? I mean, it's a bilinear form, right? In delta and in g. Why don't we try to exchange it? Sometimes you get some fun expressions, right? When you do that. So minimax theorem applies here. So we got this expression, which we call delta BV, bias variance trade-off, right? So this is a dual of the problem of finding the best estimator. Okay, so let's recap. So we get the LeCam lower bound, which is delta min TV evaluated at 1 over n, right? And delta min TV was given by this expression. And bias variance trade-off gives us an achievability bound, right? So it shows the existing estimator. And then that expression was given by this. So the only difference is that there is no one of these constraints, right? So that was the only difference. It was very surprising to us already. And then, of course, I mean, once you see this, and then if you believe in miracles, right? So then there was this miracle that actually these two functions are related to each other up to constants. So in the end, what we get is we get both achievability and converse, right, in terms of just this expression. So this was very surprising, that just by solving two-point LeCam, essentially, as an extra twist, you also get achievability, you also get existence of the estimator. Okay, so there is a gap between 1 over n, 1 over square root n, you can tighten it. Let's move on. Okay, so this is the general program, right? Whenever you have noisy observations, you want to estimate linear functional, this is what you should do, right? So just this will give you essentially tight answer for sample complexity. So let's evaluate this function for one concrete problem, which is population recovery. Okay, again, so we have distribution pi here on the set of d-dimensional hypercube, right? So we get IAD samples from pi, and then they're erased. So let's look at some animation, which took me a whole 2 hours to make, right? So. Okay, so we have the samples from this distribution. These are true answers of people, right? So this two different questions. It has 0, 1, 0, 1. So you collect the samples, right? And then you erase some portion of it, right? Okay, so then you observe these columns, right? So these are samples, and this is the dimension, right? And your job is to estimate what was the true fraction of people who generated all 0 column here, right? So the reason it's a funny problem is because you see, so for example, these two columns, I mean, it's very intuitive that what you want to do is, right, so first of all, this column, it becomes completely useless for this question, right? So you can sort of throw away those guys immediately, but this things, right, so I mean, it's a tricky question, right? Because here you see, I mean, neither of this was 0 column, right? But somehow you need to estimate. So I'm just explaining what's going on here. Okay, so let's do some reduction. So first of all, okay, estimating all 0 string is as general as estimating an arbitrary string by just XORing. Then, using the symmetry, you can convince yourself that you can only think about in those optimization problems, when you do two-point LeCam, right, you can restrict yourself to permutation invariant priors. Oh, yeah, it's 20 minutes, right, not 30. Okay, I just realized this. All right, so anyway, so, yeah, so, okay, so we need to consider, so this is the reduction which is not without loss of generality. We will only look at the statistic, which is the number of ones per column, right? So this completely should, I mean, then proving minimum TV lower bound says nothing. It's not a converse bound, right? But anyways, we will do this. I'll tell you later. Okay, so then you get this expression. I mean, this is just a problem that I described. Okay, so, right, so the only funny idea that we did here to evaluate this is to represent this vector, right? So this is just a vector indexed from 0 to d to dimension. Let's just write this polynomial. Then it turns out the action of this phi of the matrix is exactly, I mean, on this polynomial is exactly what's called composition operator. Okay, so then, okay, so the problem is that we are interested in this maximization on L1 norm of the coefficients of the polynomial. This is an ugly quantity, right? If you're a complex analyst, you don't like this quantity. What you like is the H infinity norm, meaning the maximum. But they are sister quantities, right? So let me just skip the details and convince you that you can actually replace one with another, and then you get this fantastically beautiful problem, right? So you want to evaluate among all degree d polynomials, which are bounded by 1 on the unit circle and bounded by t on the small circle. Right? You want to find the one which maximizes the value at 0. Okay. And by the way, this displaced disk is called horror disk, which I thought was a fantastic word. Okay. So, right. So you immediately get so if epsilon is less than 1/2, then this dashed disk actually crosses 0. So 0 is part of it. So you immediately get that in that case, delta of t is equal to t, which is a parametric rate. So that's the immediate answer. So which is okay. So now to solve epsilon greater than 1/2, which is a large erasure regime, which is more fun, right? So what the only twist we needed to do is to apply conformal map, right? So everybody who had first class and complex analysis, remember circles are the same as lines. So that's what we do, right? We convert the circles into these lines. So the dashed circle becomes a dashed vertical line. Okay. So and then right. So then we're trying to find the polynomial which maximizes value at 1. Subject to constraints at value at 0 and here. So then there is this famous Hadamard 3 lines theorem which shows you how to interpolate between boundaries, right? Okay, so once you apply this, you get this estimate. Delta of t is upper bounded t1 minus epsilon. And also as degree grows, I mean, Hadamard 3 line theorem is actually tight. So you can just truncate the function which such array set to get essentially, so delta of t is essentially tight. Okay, so at this point we were completely ecstatic, right? I mean, because think about it. So you prove existence of estimator by Hadamard 3-line theorem, right? So this is, I mean, I don't know. So yeah, so in my life I was not, I was euphoric like this only a few times, and this was completely, the highlight of like a month or so. But then this quickly evaporated when we started Googling, because it turns out that Moitra and Sachs also used very similar stuff. So in particular, we still tightened them, because for some reason they didn't do this conformal map. So they only estimated, they used some other theorem, which is sister theorem, Hadamard 3 circle. So their estimate was slightly less tight. But anyway, so the connection to complex analysis was there. And okay. All right, so so I wanted to tell you a few things about how the optimal estimator looks like. So okay, so first of all, for epsilon less than 1/2, because you see, so there is a catch here. Hadamard 3 lines gives us existence of estimator, but remember I said that we apply minimax, right? So this means that we are solving the dual program. So the feasible in the dual doesn't tell you anything about the primal. So it's a very strange situation where you apply some, Hadamard stuff, but it doesn't tell you anything about how estimator looks like. So to get the estimator, you actually have to, roll up your sleeves and just solve this L1 program directly. So for epsilon less than 1/2, what you need to do is you just debias. You just find the unbiased estimator. And this is how the coefficients look like, right? So basically to estimate a fraction of zeros, what you do is you count the number of zero columns, subtract 0.4 of the number of columns with 1, 1, and then add and so on. So this is what you do, right? So anyway, so for epsilon greater than 1/2, this inverse is unbounded, and that's why the rate stops being parametric, so you change to some other rate, and the estimator becomes slightly crazier. Okay, so I lied to you on a number of occasions. One occasion was when I said that L1 and H infinity can be replaced. As I said, this can be fixed. Now another thing is that we actually don't get a tight rate, because remember this 1/n versus 1/square root n. Okay, this is easily fixed by instead of going to TV and upper bounding by the triangle inequality, we just estimated Hellinger. So then there's an extra argument why we could ignore the number of zeros in the output of each column and so on. So okay, so I guess I'm out of time. So. Okay, so for the noisy operator, just let me briefly flash the result. So for the noisy population recovery, this operator becomes not a restriction operator. So f acts on polynomials by first applying this function and then multiplying by something. Now, the only fortunate coincidence here is that this function is actually an automorphism of the unit circle, of the unit disk. So you can reparameterize and get it into a slightly nicer expression, where you're trying to maximize the value at 0, subject to H infinity constraint on the unit disk, and also the product constraint everywhere. Okay, but then it turns out that you can apply some results from complex analysis, which essentially replace the usage of Hadamard 3-line stuff. And we also were lucky, because if we started with this problem, we would never be able to solve it. But because we already were primed by solving, so we knew what the optimal function there is, we just modified it a bit and fortunately got the right answer. Okay, so that's it. Thanks a lot. And then there's lots of other things which I had to skip, unfortunately.
Any questions?
Yes. Oh, yes, very good question.
Please repeat the question.
Yes, the question is, does any of this work for deletion channel? Yes, and actually this was shown by Nazarov and Perez, right? So
do they really use this?
Well, we use them, essentially, because we learned about this reference from reading Nazarov and Perez. Yes, but it's just by, okay, the operator there is completely different. So, yes, but this...
I guess my question is, can you use your framework? What you validate is different from what you...
Yeah, because it was not estimating the linear functional, right? So what was he estimating? Yes, so yeah, exactly. So it was the whole string, right? It was binary hypothesis testing. Yes. Okay, so the connection there is that they are also solving minimum TV problem, right? So they're trying to find minimum TV in the class. So anyways, but Yeah, so directly. So if by framework you mean the first third, yeah, so that's not applicable because they're not estimating the linear functional. Yeah. But that's a very, yeah, so this was another surprise. Yes. Initially our bounds were not tight here. So we had something like some exponents slightly different from the 1/3, and then we read this and said, we can tighten it. Yes. So that's a fantastic connection. Yeah. Yeah, okay.
Okay, let's thank the speakers again.